This lecture will cover polarity, which is the first part of intermolecular forces. So you need to be comfortable with polarity before you can move on to intermolecular forces. So some things you're going to want to have. You need to have a periodic table because we will be drawing Lewis structures and we will be looking at electronegativity of various elements. And then, as always, you do want to have that objective sheet out so you can kind of be aware of the things that you should be able to do. All right, so if something is polar, a lot of the times when we hear that word, maybe you're thinking of North Pole, South Pole, or the poles on a magnet. And what we think of with that is opposites. And specifically in terms of bonds, polarity means that electrons are shared unevenly, which means that we are going to have a positive end and a negative end of a bond. So what you can think of, well, first let's talk about, so that positive and negative ends of a bond is called a dipole. So you should be thinking two. So two poles, there are two ends to the bond. One side is positive, one side is negative. So electrons are going to reside closer to the electronegative atom in a bond. So let's say we have element A bonded with element B. So we know that this line here represents a bond, which represents two electrons. Now, what happens is those electrons are not shared evenly. One of these atoms, either A or B, will kind of hog the electrons. It's going to be the ones like, I'll share my electrons a little bit, but not all the way. So what we're going to see, let's say that A was more electronegative, our electrons are going to be closer to the A. It's going to hog the electrons. It's going to let B have them a little bit, but A is going to hold on to them more. So if A is holding on to the electrons more, it is going to be the negative end, which would make B the positive end. Because remember that electrons are negative. So there are two ways to represent polarity or a dipole in an atom, or in a bond, excuse me. One way is on your positive end, you could draw this little symbol with a plus sign. And then on the negative end, you draw this little symbol with a negative. So this one right here would be with your A on this example bond up here. This here would be by the B because that is your positive end. Another way, and this is how a lot of you will probably end up doing it, is you're drawing an arrow like this. So this end right here goes towards your positive one, so that kind of looks like a plus sign. And your arrow is pointing towards the negative. So points to the negative. All right, so let's go ahead and do some examples here. So not just when we're looking at bonds between two atoms, but if we're looking at an entire molecule or compound, some ways that you can definitely know something is polar if you have lone pairs on your central atom. So this should make you think, okay, we have to draw Lewis structures again. So yes, you have to draw Lewis structures. You have to draw them correctly in order to be able to do this. So the first thing, if you have lone pairs on your central atom, you are going to have a polar molecule. If you have different atoms on the central atom, you are also going to have a polar molecule. So on the last slide, you saw where you had a dipole, so you had a positive end and a negative end. So if the whole molecule has a positive end and a negative end, then the whole molecule is polar. So we're going to do some examples here so you can see how we can determine if there's a positive end and a negative end in a molecule. All right, so CH4. Step one, whenever you're trying to find polarity or your dipole, is to draw your Lewis structure. So they are not going away anytime soon. So my Lewis structure for CH4 is going to look like this. Carbon in the middle, all our hydrogens on the outside. Now what we have to do is determine my dipole between my central atom and all of my bonds to it. So my bond here, my bond here, my bond here, and here. Right, so let's change our color here. Now, remember that the head of the arrow is going to point towards the negative end of your bond. So we have CH here. Now, what you're going to have to remember is which end of this bond here is more electronegative. So that's where you have to go back to that stuff from trends and see which atom in your bond is more electronegative. So in this one, it's carbon. So we're going to draw our arrow going right at carbon. So I can draw it right on here. And it's going to be the same for all of them because all of them are carbon-hydrogen bonds. Now, what we can look at is if our bonds cancel or if our dipoles cancel. So this dipole right here is pointing towards the C. This one is as well. But since they are pointing in the same direction here, they're going to cancel each other. This one and this one, well, they're pointing in opposite directions. They're pointing towards the same atom. And then these two are also pointing in opposite directions. So our opposites are going to cancel, which means that CH4 is what we say non-polar. Because they cancel, so overall we do not have an area with a positive charge, an area with a negative charge. So let's do another example here. Let's do NH3. So if we're drawing our Lewis structure for NH3, it's going to look like this with a lone pair at the top. So here's your clue. Don't even have to draw your dipoles on this. Number one in your rules, if there's lone pairs on the central atom, there are lone pairs on my nitrogen here, it's polar. So we know that this is polar, but I want to show you the dipoles on it so you understand why it is polar. H. So here's my first bond between a nitrogen and hydrogen, and all three of them are that. Who's more electronegative? Nitrogen. Okay, your arrows are never going to point towards hydrogen. Hydrogen is not going to be electronegative. So draw my arrow towards my nitrogen, towards my nitrogen, towards my nitrogen. So this and this are going to cancel because they're pointing in opposite directions. This arrow is pointing up towards the nitrogen, which means that we have an area that's positive down here by the hydrogen. And then we have this lone pair up here. Remember, that's a lone pair of electrons, and electrons are negative, so that means we have an area that's negative up here. So we have a positive area down here, and we have a negative area up here. So this is polar because you have an area that has a negative that's slightly negative, and you have an area that is slightly positive. All right, next one, HCl. Okay, so we do have lone pairs on our central atom here, which is our chlorine. So that does make it polar, but let's just draw our dipoles so we have that practice. Chlorine is more negative. So that means that this hydrogen is slightly positive because it's not getting that equal share of electrons. This chlorine is going to be more negative. One, because of this dipole here pointing towards it, and then also because of all of these lone pairs. So since nothing cancels, we are left with a polar molecule. All right, SF6. 1, 2, 3, 4, 5, 6. All of these Fs should have lone pairs around them, but I am not going to draw all of them. Now to draw our dipoles, if you remember what the most electronegative element is, you're going to remember that it's fluorine. Anytime you have fluorine in a bond, it is going to have your dipole or your arrow pointing at that fluorine. So here and here, opposites, those are going to cancel. Opposites, those are going to cancel. And opposites, those are going to cancel. So what we're left with is a cancel with a cancel, 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 cancel. So this is non-polar. We do not have a positive or a negative region of this molecule. All right, another example, HBr. So why don't you go ahead and try that one on your own. Go ahead and pause it. All right, so you should have got something like this with your dipole pointing towards your bromine, which is going to be more electronegative than your hydrogen. So we have a slightly positive charge down here by that hydrogen. And we have a slightly negative charge down by your bromine, so that makes it polar. Another example here, BH3. If you remember, boron is one of two elements, so it's boron and beryllium, that can be stable with less than an octet. So here is our Lewis structure, so it does not have a lone pair on your central atom. So don't just add it to make it have 8. Remember that boron's okay with just having 6. So we draw towards our electronegative. All right, so we're thinking cancel, cancel. And what you might be quick to look at and say is this dipole doesn't cancel with anything. Therefore, it must be polar. However, we have to remember our VSEPR shapes. So this goes back to that. 3 bonds, 3 domains, it's trigonal planar. 3 bonds, 0 lone pairs is also trigonal planar. And something that is trigonal planar is going to be shaped like a triangle. So what my shape of this actually looks like is more something like this. And now, when you're looking at your dipoles, they're all still going to point in towards boron. But they're going in at equal angles, so they are all going to cancel with each other. So make sure that you are also, when you think, hey, something like this one right here is not canceling with something, go back to thinking about that Vesper shape. If you have something that's trigonal planar, they are going to come in at equal angles and they are going to cancel. So just keep that in mind. If you have two of the same atoms in a bond, so we have chlorine with chlorine, or we have oxygen with oxygen. So this is actually going to be a double bond on these O's, single bond on these chlorines. Now, you're probably thinking, how do I have a dipole between two things that are the same atom? Because I can't compare the electronegativity of oxygen to oxygen because it's the same. I can't compare the electronegativity of chlorine to chlorine because it's the same. So you're right in thinking that. So what we say when we have two things of the same atom bonded together is we say that it has no dipole. So there is no polarity in this because one of these chlorines is not going to share the electrons unevenly with another chlorine. Neither one has, I guess, that power to hold on to the electrons more. Okay, so that is the end of polarity. So make sure that you're comfortable with doing that. One thing that you could do just to get more practice on determining polarity is looking at your Vesper packet, and you have tons of Lewis structures drawn for you already in there that you drew when you did that packet. And just go through and you can just kind of start to draw some arrows, get yourself back in the mindset of thinking about electronegativity as well. So there is another lecture to this. It's part 2. It's going to go over the actual intermolecular forces within molecules.